this chapter, we're going to start looking at applications of derivatives. The first application we're going to look at is its application to motion problems. And we're going to begin to look at motion by talking about average speed and velocity. And then as we do this, we're also going to look at the difference between speed and velocity.
Okay, hi everybody. So now we're going to take a look at applications of derivatives. We spent a chapter looking at derivatives, the derivative rules, did all sorts of examples, taking derivatives, building them from limits and whatnot. Now we're going to spend a good chunk of the remainder of this course looking at how you can actually use derivatives to answer certain questions. And I hope that by the time we get through a lot of these different applications, that you really get a sense of what kind of a tool it is that we've given you, and how powerful this idea of a derivative is. Now, one of the most straightforward applications is that of motion. Okay, so we're gonna do a little bit of what you might call physics. Now, when my students look at me and say, "Hey, wait a minute, aren't we just doing physics in a math class?" I like to switch that around and say, you know what? Really, in physics, aren't you just doing math? Anyway, that usually gets a little bit of a laugh, but maybe not right now. Anyway, let's take a quick look and let's talk about average speed versus average velocity. Okay. Now, usually, those people that are taking a course like this or watching videos like this, your experience with physics is enough that you would know the difference between a vector quantity and a scalar quantity. What we want to do right now is talk about the difference between a vector and a scalar, but also talk about what it means when we discuss average, okay, the average speed or the average velocity. And so right now, to start off with, we're going to focus on the word average here. So if a car travels, oh boy, it's spelled wrong. Anyway, if a car travels 200 kilometers in 2 hours, we know that the average speed of the car is 100 kilometers an hour. Now, the reason for that, okay, is because average speed is calculated by taking the distance traveled over the time that has elapsed, okay? So that's the total distance traveled over the total time elapsed. Now, in reality, speed is very rarely a constant, okay? It's not like you get in the car, hit the pedal, and boom, you're up at that speed and you stay at 100 kilometers an hour for 2 hours, then all of a sudden you stop. Yeah, it's varying. It's going up and down. If you're driving down the highway, sometimes you're stuck behind people that are going slow. Sometimes it's open road, so you go a little faster and whatnot. But what we're seeing here is that the average speed ends up being, well, in this particular context, 100 kilometers an hour. Now, it is possible, though, to come up with or to engineer situations where the average speed is still 100 kilometers an hour, okay, but we do it differently. So, for example, you could drive for 1 hour at 150 kilometers per hour. You're really speeding. And then for 1 hour at 50 kilometers an hour, let's say you get stuck behind something, some construction or whatever is going on, and so everything is slowed right down. That still averages out to 100 kilometers an hour. Or you could drive for half an hour at 60 kilometers an hour, and then an hour at 120. Still speeding a bit there, but not nearly so bad as you were speeding a few minutes ago. And then you could go at 100 kilometers, for half an hour at 100 kilometers an hour. And once again, we're getting an average of 100 kilometers per hour. Okay, so again, just to summarize this again, average speed is change in distance over change in time. Okay, change in distance over change in time. Now that we've said that, we're going to want to talk about the difference between a scalar and a vector. Okay, so let's talk about a couple of definitions here. Make sure I've just got my laser pointer here. So we're talking about scalars and vectors here. Now, what a scalar is, okay, it's a magnitude without a direction. Now, if this is the first time you're being exposed to these definitions, that might seem like a weird thing to say here, but a good example here, and one that's completely appropriate, is distance, okay? Distance, or d here, is simply the total length of units traversed by an object, okay, the distance that it travels here. Now, that is sometimes all I need. I just need to know the distance that we've gone or some object has gone here. However, if I was to suggest to my class, let's say we're going to go on a field trip, and I just need you to meet me at a distance of 10 kilometers outside of town, that's not enough. That doesn't give me enough information, or doesn't give students enough information to know where to go. That's when we use a vector. A vector is a magnitude with a direction. So as soon as you attach a direction to it, like let's say 10 kilometers north, okay, 10 kilometers southeast, or just give a direction to it, then it becomes a vector. Displacement is the vector version of distance. Okay? So when we talk about the displacement that an object has, not only are we implying a distance, sorry, but also a direction here. And we use little s, okay, little italicized s there, sorry, to represent displacement. So it's the measure of where you are, okay, with respect to where you began. So there's a direction implied there. Now, when we use vectors here in a lot of cases now, and again, the assumptions kind of is that you've seen this before, but a lot of times a vector is represented with an arrow, okay, where the tail of the arrow tells you where you started, and the head of the arrow here, where you're pointing, that shows you where you're at, okay? So now that leads us to a slightly different definition here. So in this case, when we want to differentiate between the scalar quantity, distance, and we want to differentiate between the scalar quantity and the vector quantity for distance and displacement here, okay? And the reason why that's significant is because prior to this, a few moments ago, we were talking about average speed, which was the change in distance over the change in time. Now we're going to talk about average velocity. And that actually is different. I know that in our culture, we use the words speed and velocity basically synonymously, as if we can interchange them. But actually, there is a difference. As soon as you start talking about velocity, that is the change in displacement, okay, over the change in time. Okay, and so we'll use delta S over delta T to represent our average velocity. Now, something that you should note about this, though, in both cases here with average speed and average velocity, it's either the change in distance or the change in displacement over time. As we go through this, I mean, I'm sure for a lot of people that kind of makes sense right now, but as we do this more and more here, and do more with this, and we add acceleration and whatnot into this, coming back to the exam, questions like this tend to cause people problems because all of a sudden they start to do weird things with it. When I ask you for the average, let's say just say velocity, again, I mean the change in displacement over the change in time. I will often see people find the difference between velocities and then divide by the change in time. Okay? It's not. Average velocity is going to be the change in displacement over the change in time. You just got to remember this little bit right here when that question sort of pops up on the exam, just to be clear. So, okay, just to summarize this up before we start to look at this next example here, okay, distance is a magnitude without a direction. I'm just saying that we have traveled this far, okay? Displacement is throwing a direction onto the distance there. It is the distance that you are away from your starting point, but with a direction, okay, identifying kind of where you went. And then both to get speed, average speed, that's going to be the change in distance over the change in time. The average velocity will be the change in displacement over the change in time. And we're going to see that in calculus, a lot of times here, the calculus that we work with here is geared to a vector interpretation of these things, not so much the scalar interpretation. And you're going to see that for those of you that have come through and done physics, you're going to see that this is remarkably consistent with what you have seen prior to this at this point here. Anyway, we're going to take a look at some fairly simple examples just to lead into this. All right, let's take a look at this example here. It says a stone is dropped off a 200-meter cliff. Its height after t seconds is given by the function here. H of t is equal to 200 minus 4.9 t squared. Now, again, those of you that have gone through physics will recognize that negative 4.9 as 1/2 of the gravitational acceleration, okay, due to the Earth there. So what we're going to do here is we're going to find the average velocity of the stone for the following time periods. And I've got a bunch here. Now, I very likely didn't need all of those, particularly the number 4 there. But anyway, so we're going to go from 1 to 2, 1 to 1.1, 1 to 1.001, and then 0.9 to 1 here. Now, this was, I don't even really know what I was thinking at that point there, but all of these you should see are kind of, there's a limiting relation happening here. I'm kind of zeroing in on what's happening for the velocity at 1 second here. Anyway, let's take a quick look at the graph here. So this is height versus time there. So we throw the thing off. Now, bear in mind that this is not the path that the object is following. The object is just dropping straight down. This is its height as a function of time, okay? And that's going to have this kind of a curved relation to it, even though it might be dropping straight down. Now, I have got for each of the little time periods there, okay, I have got the height measure there. So this is after 1 second, it's 195.1 meters up. At 2 seconds, 180.4, and so on. And I've got the average velocities measured off for those first two. But let's go down and take a look at how that happens. Okay, so in that first time interval from 1 to 2 seconds, the average velocity is going to be the change in height over the change in time. So that is going to be the height at 2 seconds minus the height at 1 second over 2 seconds minus 1 second, change in time there. Now, I go to my height formula because I have it, and I can evaluate the height at 2 seconds. I can evaluate the height at 1 second. Now, notice at 2 seconds, it's smaller than that. So when I find the difference between them, I'm going to get negative 14.7 meters and at a change of 1 second. And that means that over that time period, on average, this is descending or dropping at 14.7 meters per second. Okay? And I hope that makes sense. And it does make sense that it would be negative, okay? Because we typically when we talk about displacement, up usually is assigned a positive value. Now, in this particular case here, that's all that it is. This is where the vector quantity comes from. Distance, in this case, is just this one directional thing. It's either up or down. We turn it into a velocity by saying it's positive going up or negative going down. That's all we needed to turn that into a vector. Now let's look at the next time period here. So 1 second to 1.1 seconds, okay? Now, average velocity, change in height over change in time. So it's the height at 1.1 second minus the height at 1 second, and then 1.1 minus 1. Find the difference. Now, this time here, the major difference here is that my time difference is just 0.1 of a second. And when I do the division, I get negative 10.29 meters per second. Okay? And again, negative because it's going down. There's my vector quantity. Now let's tighten that up just a little bit more. So between 1 and 1.001 seconds, the average velocity, again, change in height over change in time, evaluating the height at those two different times there. But this time the change in time is 0.001, and when I do the division, I get negative 9.8049 meters per second. So now you should be able to see that average velocity, okay, as that change in time gets smaller and smaller, okay, closer and closer. Basically, we're really applying a limit here and letting the time become closer and closer just to 1. We're looking at that moment when time is equal to 1. We're not there yet. Okay, we're still taking a major difference in time. It's small, but it's still a jump. But that's getting closer and closer to the negative 9.81 meters per second squared that you would assume would be the acceleration due to velocity. So at 1 second, we do assume that the velocity would be negative 9.8 meters per second. Now, we also did it for 2 to 3 seconds there. Not even so sure why I plugged that one in there, but at 3 seconds minus 2 seconds, 3 minus 2, and we get negative 24.5 meters per second is the average velocity in that time period. Okay. Now, it's it's worth noting that when I talk about 2 to 3 seconds here, that could also have been described as the third second. Okay, the third second of falling. The first second would be between 0 and 1. The second would be between 1 and 2. The third second is between 2 and 3. It's not a bad idea to kind of get familiar with that. It would be a shame to, when you get asked the question, to inadvertently grab the wrong times when you get a question like that. Now, let's go from the other direction, 0.9 to 1 second. So basically, we're going to approach 1 from both sides. And the average velocity will be the change in height over the change in time. So h of 1 now, this is the second value here, the end of our interval, minus h at 0.9 over 1 minus 0.9. Okay. Oh, sorry, that should have been right there, 0.1. Okay, and it is 0.1 when I do the calculation, but that should be 0.1. Take the difference and you get negative 9.3. And so again, it's close to that negative 9.81 that we would expect at the 1 second. Now, important to note that at this point here, when we talk about average velocity or average speed, but in this case specifically average velocity, because we're taking a macroscopic change in one variable divided by a macroscopic change in another. These are big steps. A big step in t creates a big step in h. We are in fact looking at the slope of the secant line. Okay, so you'd have some sort of curve. Okay, curve for displacement versus time. What we're looking for is the line that connects 2 points here. Now that's not quite that derivative or that tangent that we would like to see. We're going to talk about that in just a second here. So just bear in mind that this is, when we talk about velocity, average velocity, we're talking about change in displacement over the change in time, okay? And that ends up being the slope of the secant line.
Now we're going to introduce the tool of the derivative, and we're going to talk about instantaneous velocity.
Okay, everybody, now we're going to talk about instantaneous velocity, okay? And that's going to be the rate of change of displacement with respect to time. Except that now, instead of doing the slope formula per se with like the macroscopic steps here, what we're going to do is we're going to use a derivative to take microscopic steps. So we're going to be looking at essentially the velocity that we're going. Let's say you're driving on the road, the velocity that you're going now. Okay, not over a time period, not averaging it, but how fast are we going right now? Okay, that's the instantaneous velocity, and the way we get that is the first derivative of displacement. Now, sometimes you're going to see this notation used with the little dot over top. When you see a little dot like that, that's typically going to indicate a derivative with respect to time as the independent variable. Okay, but anyway, so what we're looking at here is the limit as time approaches 0 of our change in displacement. Okay, and so here's another way of looking at it, just with first principles right there. In any case here, it's going to be the limit of the average velocity. We're going to let that change in time approach 0. That's going to give us our instantaneous rate of change. So, just like it says right here, rate of change is the ratio of the change in one variable divided by the rate of change in another, okay? So dy over dx, it's exactly the same thing here. In fact, velocity is a wonderful example of an application of a derivative. So in this case here, this is a bit of notes here is just to reiterate what we had looked at in a previous lesson about the rate of change here. Now, the velocity is a good example of this, but this can be any kind of a rate of change, right? A slope is the rate at which one variable changes with respect to another. Just in our particular case here, we're going to be looking at displacement over time. Now, let's take a look at some examples. Okay, so let's take a look at an example here. So find the instantaneous velocity for question 1 when t is equal to 1 and t is equal to 2. Okay, so question number 1. Going back up, way back up to here. Here is our particular function, 200 minus 4.9 t squared. I just wanted to take a look at it again. Okay, so 200 minus 4.9 t squared. So we're throwing that rock off the cliff. let's take a quick look at what happens here. So as we've already suggested, we're going to use the limit here. We're going to use the derivative. Now, in the previous question here, we already kind of took the limit as t approached 1. And we found out that it looked like it was approaching negative 9.8 meters per second, which makes sense if you've got a bit of a physics background here and you've done stuff like this before. But it makes more sense for us in this particular context to take the derivative. So here's our height as a function of time. There's our independent variable. And when you take the derivative, okay, we're going to get velocity, which is the derivative of height with respect to time. Again, that's what that little dot means. Bring down the 2, multiply by the coefficient, and we get negative 9.8 t. Okay, now not exactly the negative 9.81, so on that you'd expect when you're working with acceleration due to gravity, but that's okay. We're just working with some approximate values here. And when you plug 1 into that, you will in fact get negative 9.8 meters per second. Okay, that's exactly what we were expecting. Now, if you want to figure out what the velocity is after 2 seconds, all you got to do is take this velocity formula and plug in that time for 2. Whoops, down to here. That's all you got to do. Makes it very, very straightforward. So we plug t is equal to 2. So the velocity or the derivative of displacement or height with respect to time, negative 9.8 times 2, and we get negative 19.6 meters per second. Now, in that previous question, if we had more time, it would have been fun to have sort of taken the limit as time approaches as 2 seconds, just to show that this pops up. But anyway, that gives you an idea of how that works. It's no different than what we were doing before. The derivative work is exactly the same, except that our independent variable is time. Other than that, it's working exactly the same. Okay, let's take a look at one more example here. So given that a particle's displacement can be expressed as displacement equals, then here we go, again, as a function of time, we want to find its average velocity during the 3rd second, and then its instantaneous velocity when t is equal to 2 here. Now, it's important to catch this. Now, when we do the average velocity, okay, remember that's going to be change in displacement over the change in time without the limit. Okay, the limit is going to give us an instantaneous velocity. Without the limit, we get the average velocity. Now, over the 3rd second here, let's just take a quick look at what that might look like here, because I know that sometimes this creates a little bit of confusion here. That little bit of vocabulary here. So what I'm going to do is just really quickly draw out a number line. Hopefully this the machine will kick in here in a second and I can do this for you. Okay, so we're talking about it says here the 3rd second. Now, when you are measuring, see, it doesn't want. Okay, here we go. When you're measuring time here, we're going to take a quick look at our number line. Oops. Okay, here we go. At our number line, here we go. Nope. So here's where time starts. Time is equal to 0, time is equal to 1, 2, and 3. So right here, this is our 1st second, starting at time equals 0, going up to time equals 1. This is our second, starting at time is equal to 1, going to time is equal to 2. And here's our 3rd second, and this is the one that we're referring to right here. So this is going to be in between t is equal to 2 and t is equal to 3. Okay. Now, the only way that you're going to be able to answer that question is if you recognize that that's actually what it's saying. So now when we come back to this here, to get our average velocity, it's displacement at 3 seconds minus the displacement at 2 seconds over 3 minus 2. And you can plug that in really quickly. You get 41 minus 22 over 2. Sorry, over 1. Wow, over 1. And your average velocity is 19 meters per second. Now, that's relatively close to what we were talking about before here. That's okay. As that gets smaller, that gets more exact. If you want the instantaneous velocity, what we got to do is take the derivative. So the derivative of 5t squared minus 6t will be 10t minus 6. And then we are going to evaluate this. That's what that line means. We're going to evaluate this where x is equal to 2. When you plug that in, you get 14 meters per second. Okay, so bear in mind that the derivative, the first derivative, applies to all sorts of rates of change. This is just a really great example of one. And that when you take the derivative, okay, of a displacement graph, what you're getting is the slope of the tangent to the displacement graph. And that we interpret as the velocity at that specific point in time. Okay. Hopefully that makes a bit of sense here. In the next couple of lessons, we're going to talk specifically about velocity and acceleration and build on these two ideas.